There is something deeply strange about the night sky, and it has nothing to do with the stars you can see. It has everything to do with the ones you can't. Not the stars obscured by clouds, not the ones too dim for the naked eye, but something more fundamental than that. A concealment woven into the very fabric of reality itself. What if the universe isn't simply vast and complex and difficult to understand, but is instead, in some deliberate and structural sense, partially hidden from you? Not hidden the way a secret is kept by a person who chose silence, but hidden the way a painting hides the canvas beneath it. Hidden the way a word hides the silence that surrounds it. You have been looking at the sky your entire life, and somewhere in the back of your mind a quiet question has been forming. A question you probably haven't put into words yet, because the words feel too large, too strange, too close to something that can't be easily dismissed. But that question is there. It has always been there, and it is starting to become louder. The feeling begins gently. It doesn't arrive with a dramatic realization or a sudden shock. It comes the way dawn comes, slowly, almost imperceptibly, until the moment you realize the darkness has changed. You might be standing outside at night, looking up at what appears to be an immensity of stars, and something very quiet inside you asks, "Is this everything? Is this really all of it?" The question seems almost childish at first, almost naive, the kind of thing a person might dismiss as mere wonder, as the natural awe that comes from staring into something vast. But the question doesn't go away, and the more you learn, the more it doesn't go away. Because science, the very discipline we've built to answer such questions, has spent the last century quietly discovering that the answer is no. This is not everything, not even close. What you see when you look at the universe is not the whole picture. It is not even the majority of the picture. It is something much more like the tip of an iceberg floating in an ocean so deep that the bottom has never been, and may never be, reached. You have to understand that for most of human history, we believed we could see the universe. We believed that what was visible was what existed. The ancient astronomers watched the stars with naked eyes and built entire civilizations around what they observed. Calendars, mythologies, navigational systems, religious architectures all mapped onto the visible sky. They were confident, those ancient observers, in the way that people are confident when their world appears coherent and complete. The stars moved in patterns. The planets traced predictable arcs. The moon waxed and waned with the kind of rhythmic reliability that seemed to confirm, yes, the universe is ordered, and yes, we can observe it, and yes, observation is enough. That confidence wasn't foolishness. It was simply the natural human response to a universe that appeared in every measurable way to be visible, to be present, to be transparent. Then came the telescope. And the telescope did something extraordinary. It didn't just magnify what we already knew existed. It revealed that existence itself was far larger than we had imagined. Galileo turned his glass toward the heavens, and suddenly, Jupiter had moons. The Milky Way resolved into individual stars, and the universe grew by orders of magnitude in a single night. That moment should have been the beginning of humility. It should have been the moment humanity realized that the universe will always be larger than our instruments. But instead, something different happened. We became more confident, not less. We built better telescopes, and the universe grew larger still. And every time it grew, we were proud. Proud that we could see it growing. Proud that our instruments were keeping pace with reality's expansion. Proud that wherever we looked, we could find something to see. We looked outward and found galaxies. We looked deeper and found galaxy clusters. We looked further still and found the large-scale structure of the cosmos. Vast filaments of matter stretching across hundreds of millions of light years, forming a web so enormous that the mind can barely contain it. We looked and we saw, and seeing felt like knowing. But here's the thing about telescopes, the thing that gets lost in the excitement of every new discovery. A telescope only shows you what emits light, or reflects light, or interacts with light in some way. The entire architecture of our observational universe, every galaxy we've cataloged, every nebula we've photographed, every star we've named, all of it is built from light. We are, in the most literal and profound sense, creatures who see by light, who think by light, who have built every scientific instrument in history around the detection of light and its cousins across the electromagnetic spectrum, radio waves, X-rays, infrared, ultraviolet. Our entire picture of the cosmos is a picture painted in light. And here is where the quiet unease begins to arrive if you let it. What if the universe is not primarily made of light? What if light, the medium through which we perceive everything, is not the primary substance of reality, but merely the surface layer? What if most of what exists doesn't interact with light at all? This is not a hypothetical question. This is not a philosophical speculation. This is the conclusion that modern physics has been quietly, methodically, and unavoidably arriving at for the better part of a century. The universe, as best we can determine, is not made mostly of the stuff you can see. The atoms, the molecules, the stars and planets and galaxies that fill your field of vision and your scientific instruments, all of it, all the visible matter in the universe, adds up to approximately 5% of what actually exists. 5%. When you look at the sky, when you look at the full, breathtaking, incomprehensible expanse of the observable universe, with every telescope humanity has ever built, you are seeing 5% of what is there. The other 95% is, in the most technical and precise sense of the word, invisible to you. You are right now immersed in something you cannot see, cannot touch, cannot detect with any instrument you have ever built. And the strangest part, the part that should give you pause, is that we know it's there. We know it's there precisely because of what it does to the 5% we can see. The story of how we discovered we were blind begins not with a dramatic experiment, but with a woman watching galaxies spin. Her name was Vera Rubin, and in the 1960s and 1970s, she was doing what might seem like straightforward astronomy, measuring how fast stars move as they orbit the centers of their galaxies. This is the kind of measurement that should produce a simple, predictable result. If you think about how our solar system works, the planets closest to the sun orbit fastest because they're caught in the sun's strongest gravitational grip. Move further out and orbital speed decreases. Jupiter is slower than Earth. Saturn is slower than Jupiter. This pattern, called Keplerian rotation, after Johannes Kepler, who first described it, is one of the most reliable and well-established patterns in all of physics. It should apply everywhere. It should apply to galaxies. When Vera Rubin measured the rotation of stars within galaxies, she expected to see the same pattern. Stars in the outer regions of a galaxy moving more slowly than stars near the center, because most of the galaxy's mass is concentrated at the center, and the gravitational influence should diminish with distance. What she found instead stopped her cold. The stars in the outer edges of galaxies were moving just as fast as the stars near the center, sometimes faster. The rotation curves, the graphs that tracked orbital speed against distance from the galactic center, were flat, not sloping downward the way physics predicted, flat, as if something invisible was wrapped around every galaxy, providing gravitational mass that the visible stars and gas couldn't account for. As if each galaxy was not a collection of stars embedded in empty space, but a collection of stars embedded in something much larger, something that didn't glow, something that couldn't be photographed, something that affected gravity without interacting with light. The first response from the scientific community was predictable. She must have made a mistake. But Rubin was meticulous, and the measurements were repeated and refined and confirmed again and again across dozens of galaxies, then hundreds. The flat rotation curves were real. The missing mass was real, and the universe had just told us something about itself that we desperately did not want to hear. What you can see is not where the gravity is. There is more, and it is hidden. This hidden mass, this invisible gravitational presence, was eventually named dark matter. The word dark is slightly misleading, because dark typically implies something that is simply obscured or in shadow. Dark matter is not in shadow. It does not have a shadow. It doesn't emit light. It doesn't reflect light. It doesn't absorb light. As far as we can tell, it doesn't interact with the electromagnetic force at all. The only way it makes itself known is through gravity. It bends space. It holds galaxies together. It sculpts the large-scale structure of the cosmos. Without it, galaxies as we know them could not exist. They would fly apart, shredding themselves into empty voids. Dark matter is, in a very literal sense, the skeleton of the visible universe. The galaxies you see in those breathtaking Hubble photographs, they are decorations on a framework you cannot see. The universe's architecture is invisible. The bones are hidden. You are looking at skin and calling it a body. And dark matter is only the beginning. If you thought the discovery of invisible gravitational mass was unsettling, consider what was discovered in 1998, when two independent teams of astrophysicists were studying supernovae, the enormous explosions that occur when certain types of stars die. Supernovae are useful to astronomers because they produce a relatively consistent amount of light. They are what astronomers call standard candles, objects whose intrinsic brightness is predictable enough that you can use them to measure cosmic distances. By measuring how bright a distant supernova appears versus how bright it actually is, you can calculate how far away it is. This is the kind of measurement that ought to produce a simple story about the universe expanding the way everything expands after an explosion. which is to say, slowly. The initial bang was enormous, yes, but gravity should be pulling everything back, slowing the expansion gradually over billions of years. The story everyone expected was a universe coasting, maybe even beginning to decelerate, but that is not what the supernovae said. What the supernovae said was something else entirely, something that contradicted every expectation, something so strange that the researchers who first discovered it spent months checking their data, convinced they had made an error, because surely reality could not behave this way. The distant supernovae were dimmer than they should have been, not slightly dimmer, measurably, significantly dimmer, in a way that could only be explained if the universe was not decelerating but accelerating. The expansion of space was not slowing down, it was speeding up. The universe was not coasting to rest the way a thrown ball does. It was accelerating outward, faster and faster, as if something was pushing against gravity itself, as if there was a force embedded in the very fabric of space that was actively driving everything apart. This force, this pressure, this invisible energy woven into the vacuum of space, we named it dark energy. And when we calculated how much of it there must be to produce the acceleration we observe, the number was staggering. Dark energy accounts for approximately 68% of everything. Dark matter accounts for approximately 27%. All the visible matter in the universe, every star, every planet, every galaxy, everything you have ever seen or could see, adds up to 5%. We named 95% of the universe dark because that is the most honest word we have for it. We cannot see it, we don't know what it is, and we are working almost entirely in the dark. Pause for a moment and let that actually land. Not as a fact you file away, not as a number you nod at because you've heard it before, but as a genuine confrontation with what it means. You are made of atoms. The chair or surface beneath you is made of atoms. The air you're breathing, the planet you're standing on, the sun that keeps you warm, the entire Milky Way galaxy with its hundreds of billions of stars, all of it, every last atom of it, is 5% of what exists. The universe is 95% composed of things we cannot see, cannot detect, cannot directly measure, cannot explain. We have two words for the 95%, dark matter and dark energy. But naming something is not the same as understanding it. We have not detected a single dark matter particle in a direct laboratory experiment, despite decades of increasingly sensitive searches. We don't know what dark energy is at a fundamental level. We don't know if these two darks are related. We don't know if our description of them is even close to accurate. We have labels for the unknown, that is all. And somehow this extraordinary admission, that the universe is 95% invisible to us, has not shaken our confidence the way it probably should have. It's worth sitting with the question of why that is. Why hasn't the discovery that 95% of the universe is hidden from us fundamentally altered the way we talk about our knowledge of the cosmos? Part of the answer is psychological. Humans are remarkably good at accommodating disturbing information by reframing it as a solved problem. We discovered dark matter and dark energy, gave them names, incorporated them into our models, and moved on. We built what's called the Standard Model of Cosmology, the Lambda CDM model, which includes dark matter and dark energy as parameters, and it works, meaning it makes predictions about the large-scale structure of the universe that match observations reasonably well. And so the hidden 95% gets tucked into the model, represented by Greek letters and free parameters, and the model gets called the Standard Model. And suddenly it feels settled, known, resolved. But it isn't. A label is not an explanation. A parameter is not a physical understanding. We have measured the shape of the shadow. We have not seen the thing that casts it. And here is where the pattern starts to emerge, because dark matter and dark energy are not the only places where the universe has refused to reveal itself. They are not anomalies in an otherwise transparent cosmos. They are symptoms of something systematic, something that runs through science at every scale. A consistent, recurring encounter with the limit of what can be seen, what can be measured, what can be known. Once you start looking for this pattern, you find it everywhere. It appears in cosmology, yes, but it also appears in quantum physics, in the structure of space and time, in the nature of information, in the way reality behaves when it is observed. The universe's opacity is not localized. It is not confined to the question of what dark matter is made of. It is a feature, possibly the defining feature, of reality as we experience it from the inside. Consider what happens when you try to look at the universe from the very beginning. The Big Bang Theory tells us that the cosmos originated approximately 13.8 billion years ago, in a state of extraordinary density and temperature. In the first moments after the Big Bang, The universe was so hot and dense that matter and energy were a churning plasma, particles smashing into each other so rapidly that light couldn't travel freely. The universe was opaque. Light was trapped. For roughly 380,000 years after the Big Bang, there was no transparency, no visibility, no way for light to escape and carry information outward. The universe was a fog. Then, as the universe cooled, electrons and protons combined to form neutral hydrogen atoms, and suddenly the fog lifted. Light streamed outward. That light, called the cosmic microwave background radiation, is still traveling today, and we can detect it. It is the oldest light in the universe, but it is also a wall, because everything that happened before the universe became transparent, all of those first 380,000 years, is permanently hidden from direct optical observation. The universe's opaque youth is inaccessible to us not because our instruments are insufficiently powerful, but because physics itself sealed that era away behind a wall of light. We cannot see the beginning, we can only infer it, and the cosmic microwave background, the oldest light we can see, the relic radiation from when the universe first became transparent, is itself a source of deep mystery. When we map it, when we measure the tiny temperature fluctuations across the sky that record the early structure of the cosmos, we find that it is almost perfectly uniform. Almost. There are tiny variations, ripples in the temperature of this ancient radiation, and those ripples seeded all the structure we see today. Galaxies, galaxy clusters, cosmic filaments, all of it grew from those tiny quantum fluctuations frozen into the fabric of the early universe. This much we understand, or believe we understand. But when you look at the cosmic microwave background carefully, when you look at the large-scale patterns rather than the small-scale ripples, you find something that doesn't fit, something anomalous. There is a feature in the data that cosmologists have come to call the axis of evil. It's a name given with some humor and some unease, because what it describes shouldn't be there. The large-scale structure of the CMB, the way the temperature variations are oriented across the entire sky, appears to align along a preferred direction. Not randomly scattered, as theory predicts, but aligned, as if the universe has a preferred axis, as if something imposed a direction on the cosmos before we could see it. This alignment is statistically unlikely enough that it shouldn't be there by chance, and no one knows why it is there. You might think, perhaps it's a measurement artifact, a bias in our instruments, some systematic error in the data collection, and you'd be reasonable to think that. Scientists thought that too, initially. The WMAP satellite that first mapped the CMB in detail was scrutinized exhaustively for possible errors. Then the Planck satellite, a more advanced instrument, remapped the CMB with greater precision, and the axis of evil was still there, clearer actually, more precisely defined. It persisted across two different spacecraft, two different teams, two different sets of instruments. It's real, in the sense that it is genuinely present in the data. What it means, whether it reflects something about the actual geometry of the universe, or something about the physics of the early cosmos that we don't understand, or something else entirely, is a question that remains open. It is a pattern in the oldest light we can see, a pattern that points to something and we don't know what it's pointing at. The universe left a mark on itself. We can read that it's a mark. We cannot read what it says. The unease deepens when you consider the Hubble tension. This is perhaps the most discussed and most significant discrepancy in modern cosmology, a disagreement so sharp, so well documented, and so stubbornly persistent that it has forced physicists to genuinely question whether our standard model of cosmology is incomplete. The Hubble constant is the rate at which the universe is expanding, the number that tells you how fast a galaxy is moving away from you based on its distance. It should be a single, consistent number, because the expansion rate of the universe is a fundamental property of the cosmos. But when physicists measure it two different ways, using the cosmic microwave background to infer the expansion rate from the early universe, versus using nearby standard candles like Cepheid variable stars and supernovae to measure the expansion rate directly in the local universe, they get different answers. Not slightly different, significantly different, with a gap that has grown more pronounced as measurements have become more precise, not less. The tension has not resolved as our instruments improved. It has sharpened, which means it is almost certainly not a measurement error. Something is genuinely discrepant. The universe seems to be expanding at different rates depending on how you measure it, which should be impossible if our standard model is correct. The Hubble tension is the kind of problem that makes physicists uncomfortable in a very specific way. It's not a mystery in the sense of something unexplained and exotic. It's a disagreement between two extremely well-established measurement techniques. both of which have been checked and rechecked and refined by teams of extremely careful scientists. When two well-tested methods of measuring the same thing give different answers, there are limited possibilities. Either one or both measurements have systematic errors we haven't identified, which becomes increasingly unlikely as the measurements get more precise, or our model is wrong. There is something about the universe's history or physics that we are missing, some ingredient that is absent from our equations, some behavior of space and time or matter and energy that we have not accounted for. Or, most haunting of all, the universe actually does expand at different rates at different times and scales, and our model, which assumes a simple, consistent expansion, is an oversimplification that papers over something deeper and stranger. Each of these possibilities implies the same fundamental thing: we are missing something. The universe is not fully visible to us, not fully transparent to our models, not fully captured by our equations. And then there is the matter of the Great Attractor. In the 1970s and 1980s, astronomers noticed that our galaxy, the Milky Way, was moving. Not just the ordinary motion of rotation around the galactic center, not just the Milky Way's motion within the local group of galaxies, but an additional motion, a pull, a drift towards something. Our entire galaxy, along with dozens of other nearby galaxies, is being drawn toward a region of space roughly 150 to 250 million light-years away. Something immense is pulling us. When astronomers tried to look at the region we seem to be moving toward, they found it sits squarely behind the zone of avoidance, the region of the sky that is blocked by the disk of our own Milky Way galaxy, where dust and gas are so dense that optical telescopes cannot see through. The Great Attractor hides behind our own galaxy. It pulls us with the gravity of something equivalent to tens of thousands of galaxies, and for decades we could not even see what it was, because the universe had arranged things such that our view was blocked. Even now, with radio telescopes and X-ray observations that can peer through some of the dust, the full picture remains elusive. We are falling towards something. We know approximately where it is. We do not fully understand what it is. The universe arranged this situation as if on purpose, placing the most gravitationally influential nearby structure directly behind the part of the sky we can't see. There is something about that image, a galaxy falling towards something it cannot see, that carries a weight beyond astronomy. It is an image that speaks to something broader, something about the relationship between any observer and the reality they are embedded in. You cannot step outside the Milky Way to get a clear view of what's pulling it. You are inside it, moving with it, drawn along by the same invisible force. Your perspective is not neutral. Your position is not chosen. You are already inside the situation you are trying to understand, and the situation is already moving you before you have a chance to understand it. This is not just a problem in astrophysics. This is a problem in epistemology, the study of how we know what we know, and it runs very deep. Consider for a moment the observable universe. We talk about the observable universe as if it's simply the universe we can see, the part within range of our telescopes. And in a sense, that's true. But the reason the observable universe has a boundary isn't just a matter of telescope power. The boundary exists because light travels at a finite speed, and the universe has a finite age. Light from very distant regions of the universe hasn't had time to reach us yet. The edge of the observable universe and the cosmic horizon is not a wall in space. It is a wall in time. Beyond it, space continues, possibly infinitely, but information from those regions cannot reach us, because the universe is not old enough for that light to have traveled the distance, and because the universe is accelerating in its expansion, many of those regions will never be visible to us. The light from them will never arrive. They will recede faster than their light can travel toward us, disappearing behind a horizon that is expanding in a way that permanently cuts off portions of reality. The universe has a built-in blindness, a structural limit on what any observer inside it can ever know. This is not a temporary limitation. It is permanent. Physics has written it into the cosmos. There are things that exist that will never be accessible to you, not because you haven't looked hard enough, but because the universe is designed in such a way that they are hidden by structure itself. Now bring that closer. Bring it all the way down from the cosmic scale to the smallest scales physics can describe, because the same theme, hidden, inaccessible, fundamentally obscured reality, appears at the quantum level with equal force and equal strangeness. Quantum mechanics is, in its essence, a theory about what can and cannot be known about a physical system. It is not a theory about what exists and what doesn't. It is a theory about observability itself, and what it says about observability is deeply unsettling. At the quantum level, particles do not have definite properties, definite positions, definite momenta. definite states, when they are not being observed. Instead, they exist in superpositions, combinations of multiple possible states, all of which are real in some sense, none of which is actualized until a measurement is made. The act of observation does not simply reveal what was already there. The act of observation participates in creating what is there. Reality, at the most fundamental level we can probe, is not fully formed until it is looked at. The Heisenberg uncertainty principle, perhaps the most famous equation in quantum mechanics, says something precise and extraordinary. You cannot simultaneously know both the position and the momentum of a particle to arbitrary precision. The more precisely you measure one, the less precisely you can know the other. This is not a statement about the limits of your instruments. This is not saying that if you built a better measuring device you could get around it. It is a statement about reality itself. Precision in one domain necessarily creates uncertainty in another. Knowledge of one property necessarily obscures another. The universe, at its most fundamental level, refuses to be fully defined. Certainty in one dimension costs certainty in another, and no amount of cleverness or technological improvement can change this. The uncertainty is not in your measurements, it is in the fabric of existence. Reality is, at its foundations, irreducibly indeterminate, and this is not a bug. This is a feature that means the universe, even at the scale of its smallest components, maintains a kind of hiddenness, a final layer that cannot be peeled back. And then there is the measurement problem. This is perhaps the deepest and most philosophically unsettling problem in all of physics, a problem that has resisted clean resolution for nearly a century, despite the best efforts of the most brilliant minds in the history of science. Quantum mechanics describes physical systems using a mathematical object called the wave function. The wave function encodes all the possible states a system can be in and the probability of each. When you make a measurement, the wave function collapses to a single definite state, the outcome you observe. But the equations of quantum mechanics, the Schrödinger equation that governs how wave functions evolve, never describe collapse. They describe smooth, continuous, deterministic evolution of a wave function. There is nothing in the equations that produces collapse. The collapse is added by hand as an additional postulate, and it is never explained. What causes the collapse? What constitutes a measurement? What distinguishes an observer from a non-observer? Where exactly does the quantum world end and the classical world of definite, observable things begin? No one knows. This is the measurement problem, and despite a century of proposals, Copenhagen interpretation, many worlds interpretation, pilot wave theory, relational quantum mechanics, cubism, none of these interpretations has achieved consensus, and all of them leave something profound unexplained. The gap between quantum reality and observed reality is a gap that physics has not closed. It may not be closable. The transition from the hidden quantum world to the visible classical world remains, in the deepest sense, mysterious. The many worlds interpretation deserves a moment here, because it pushes the hidden universe theme into territory that is simultaneously mathematical, philosophical, and deeply strange. The many worlds interpretation, proposed by Hugh Everett in 1957, takes the Schrödinger equation at face value. If the equations never describe collapse, then collapse doesn't happen. Instead, every time a quantum event could go multiple ways, the universe branches. It splits into multiple copies, one for each possible outcome, all of which are equally real. Every quantum measurement you have ever made, every quantum event that has ever occurred anywhere in the universe, resulted not in a single outcome, but in a branching of reality into multiple versions, all coexisting, all equally real, none aware of the others. You, right now, are one branch. There are, according to this view, an almost incomprehensible number of other branches, other versions of the universe, other versions of you, that are just as real as this one, that exist right now, but that are permanently hidden from you. They are not in a distant part of space. They are not in the future or the past. They are, in some sense, here, parallel to this moment, inaccessible not by distance, but by the structure of quantum mechanics itself. If the many worlds interpretation is correct, and there are serious physicists who believe it is, then the universe is not 95% hidden from you. It is almost infinitely hidden. What you can see is a vanishingly small sliver of what exists. You might push back here. You might say, many worlds is just one interpretation, and unproven, and perhaps not to be taken too seriously, and you'd be reasonable, but here's what's striking. Every serious interpretation of quantum mechanics Every attempt to make sense of what the equations are actually describing involves some kind of hidden, inaccessible reality. The Copenhagen interpretation hides reality behind the act of measurement, declaring that questions about what exists before observation are simply meaningless. The pilot wave theory, also called Bohmian mechanics, posits a hidden pilot wave guiding particle positions, a wave that is real but unmeasurable in any direct sense. Relational quantum mechanics says the properties of a system are only defined relative to a specific observer, hiding the idea that there is any observer-independent reality at all. Cubism says the wave function is not a description of the world, but a description of an agent's beliefs, hiding the world itself behind a wall of epistemology. Every interpretation of quantum mechanics, whatever form it takes, tells you the same thing. The full reality behind what you observe is not accessible to you. You get the surface. You get the outcomes. What lies beneath remains, in some important sense, hidden. Step back again and think about all of this together, because the pattern is undeniable when you see it clearly. Dark matter, 95% of the universe's mass energy, is invisible to every instrument we have built. The cosmic horizon, large portions of the universe are permanently beyond any possible observation. The quantum measurement problem, the foundation of physical reality, is inaccessible, hidden behind the act of observation. The wave functions collapse. The transition from quantum possibility to classical actuality is unexplained and perhaps unexplainable. The Hubble tension, our best model of the universe, contradicts itself in ways that suggest something fundamental is missing. The axis of evil, the oldest light in the universe, carries patterns we cannot explain. The great attractor, we are being pulled toward something we cannot fully see. These are not disconnected puzzles. They are not separate rooms in the house of knowledge, each with its own resolution and progress. They are windows in the same building, and through all of them you can see the same landscape, a reality that is vast and complex and structured, but that does not allow itself to be fully seen. This is a pattern, and patterns in science mean something. Patterns mean that there might be a deeper explanation. Patterns mean that the separate mysteries might be expressions of a single, more fundamental truth. And the truth that the pattern seems to be pointing toward, the thing that would explain why the universe is hidden at so many different scales and in so many different ways, is something that science is only beginning to have the language to discuss. The possibility is this, that our universe is not the whole of reality, that what we call the observable universe, even including all the dark matter and dark energy and undetectable quantum states, is itself embedded in something larger, something more complex, something that doesn't interact with our instruments in any direct way, something that is, in the most fundamental sense, outside the frame of everything we can perceive. This is not mysticism. This is not speculation. This is where the mathematics is pointing, and the mathematics is very strange. String theory, whatever you might think of it, however controversial it may be as a physical theory, has one prediction that is strikingly relevant here. String theory requires the existence of extra dimensions of space beyond the three we experience. Not metaphorical dimensions, not dimensions in some philosophical sense. Additional, literal dimensions of space, compactified at tiny scales too small for any existing instrument to probe, but real, with physical consequences. If string theory is correct, and it remains unverified but also unmathematically inconsistent, which is part of why physicists continue to take it seriously, then the three-dimensional space you inhabit is a surface, a brain, embedded in a higher dimensional space called the bulk. Other brains may exist, parallel universes separated from ours not by distance in ordinary space but by distance in the extra dimensions. These universes could be extraordinarily close, nanometers away in the extra-dimensional sense, and yet completely invisible to us, because all the particles and forces we know about are confined to our brain. Only gravity, according to some versions of string theory, can leak between brains, which would mean that the gravitational anomalies we observe, dark matter, the great attractor, the structure of the cosmos, might be partially caused by matter on another brain, a brain we cannot see, interacting with our universe only through the one force that escapes into the bulk. Think about the weight of that image. Another universe, another brain, populated perhaps with structures as complex as our own, stars, matter, perhaps organized matter, separated from you not by billions of light years but by a distance so small it makes the size of a proton look enormous, yet completely inaccessible, completely invisible, its matter passing through you without interaction, its light not touching you, its existence only announced to your universe by the way its gravity tugs very subtly on the matter you can see. You would never know it was there, not through any direct measurement, not through any observation. You could only infer it from the shapes gravity draws in your world, from the way galaxies spin, from the way light bends around things you cannot see, from the subtle tugs and pulls and anomalies in the gravitational map of the cosmos. Dark matter in this scenario is not a particle you haven't found yet. It is the shadow of a world you cannot access. Of course, this is speculative. String theory and brain cosmology are speculative, and responsible science requires acknowledging that. But speculation in physics is not the same as fantasy. It is the leading edge of inquiry, the place where mathematics extends beyond confirmed observation into territory that future observations might one day reach. And what is extraordinary about speculative physics today, what separates it from mere philosophy, is that the speculations are mathematically constrained. They don't allow anything. They predict specific things, and those predictions can be tested, if not always with current technology. The fact that these mathematical frameworks consistently point toward hidden structures, hidden dimensions, hidden layers of reality, that's not nothing. That's the universe's own mathematics hinting at its own incompleteness. The equations keep pointing beyond themselves. They keep demanding more variables, more dimensions, more components than we can directly observe. It's as if the universe is writing equations on the visible wall, and the equations keep referencing pages you're not allowed to read. Now enter a different kind of hidden structure, one that operates not at the level of cosmological scale or quantum foundation, but at the level of information itself. Physicists have been grappling for decades with a question that sounds almost too simple to be profound. What happens to information when it falls into a black hole? The question matters because one of the most sacred principles in physics is that information is conserved. Information cannot be created or destroyed. The total informational content of the universe, the complete description of every particle, every field, every quantum state, must remain constant, even as it transforms, shifts, rearranges itself through every physical process. This principle, called unitarity, is foundational. It underlies quantum mechanics. It underlies thermodynamics. It underlies our entire framework for understanding how the universe evolves over time. And then Stephen Hawking came along with a calculation that threatened to destroy it entirely. In 1974, Hawking showed that black holes are not truly black. They radiate through a quantum mechanical process at the event horizon, the point of no return beyond which nothing, not even light, can escape. Black holes emit a faint thermal radiation that slowly carries away their mass. Over astronomical timescales, a black hole can evaporate completely, shrinking and shrinking until it vanishes in a final burst of radiation. This is Hawking radiation, and it is one of the most celebrated predictions in theoretical physics, a beautiful intersection of quantum mechanics and general relativity. But it came with a devastating problem. The radiation that Hawking calculated is thermal. It is random, featureless, carrying no information about what fell into the black hole, which means that if a black hole forms, accumulates matter, and then evaporates away, all the information about that matter, every quantum state, every bit of description about every particle that ever fell in, is gone, destroyed. This is the black hole information paradox, and it is one of the deepest unsolved problems in all of theoretical physics. If information can be destroyed in a black hole, then the fundamental principle of information conservation is violated. Quantum mechanics breaks down, and something essential about the structure of reality, the idea that the past is fully encoded in the present, that the universe carries its own complete description, is no longer true. The attempts to resolve the information paradox have led physicists into some of the strangest and most profound territory in the history of science. One of the most radical proposals is the holographic principle, the idea, first suggested by Gerard 't Hooft and Leonard Susskind, and later formalized in the AD-CFT correspondence by Juan Maldacena, that all the information in a volume of space is actually encoded on the boundary of that volume, on a lower dimensional surface surrounding it like a hologram. Our three-dimensional universe, with all its matter and energy and complexity, might actually be a kind of holographic projection of information encoded on a two-dimensional surface, the cosmic horizon, perhaps, or some more abstract boundary of reality. This is not a metaphor. Maldacena's calculation is precise, mathematical, and has been tested extensively in theoretical contexts. The holographic principle is taken seriously by thousands of physicists, and what it implies is extraordinary. The reality you inhabit, three-dimensional, apparently solid, apparently deep, might be a projection, a higher dimensional encoding of information that lives on a surface you cannot directly access. You are, potentially, a hologram. The universe you navigate might be a shadow of something more fundamental, something two-dimensional, something hidden behind the apparent depth of three-dimensional space. The holographic principle doesn't make the three-dimensional world less real. The hologram is real. Your experiences are real. The physics you can measure is real. But it suggests that what you see, what you experience as the solid, three-dimensional reality of the cosmos, is a rendering, a projection, something that emerges from a deeper, hidden informational substrate that you cannot directly perceive. And this means that reality has layers you cannot access, not just at the cosmic scale of dark energy, not just at the quantum scale of wave functions, but at the most basic informational level. The description of reality is hidden from the reality itself. The code is hidden from the program it generates. And if the universe is a kind of holographic projection, then a question that once seemed purely philosophical becomes physically urgent. What is the nature of the substrate it's projected from? What is the deeper layer, the fundamental informational structure from which the three-dimensional universe emerges? We don't know. We have glimpses, mathematical structures, theoretical frameworks, suggestive calculations. But the substrate itself, the deep layer of reality from which everything else might emerge, is not visible to us. It may never be directly visible to us. We are like characters in a film who have become sophisticated enough to notice that their world is projected, but who cannot step outside the screen to see the projector. We are inside the projection, made of the projection, perceiving only the projection. The mechanism behind it is hidden behind the screen. Let's talk about the vacuum. Not the vacuum in a philosophical sense, and not the vacuum of outer space in the ordinary sense, but the quantum vacuum, the ground state of quantum fields, the state of lowest possible energy. In classical physics, a vacuum is simply emptiness, nothing. In quantum physics, the vacuum is anything but empty. Because of the Heisenberg uncertainty principle, even the lowest energy state of a quantum field is not perfectly calm. Virtual particles and particle-antiparticle pairs spontaneously pop into existence and annihilate each other so rapidly that they can't be directly detected. They are not real particles in the ordinary sense. They are fluctuations in the quantum field, ephemeral and invisible, present and absent in the same instant. But they have real, measurable effects. The Casimir effect, the attraction between two uncharged metal plates placed very close together in a vacuum, is caused by virtual particles. The Lamb shift, a tiny displacement in the energy levels of hydrogen atoms, is caused by virtual particles interacting with electrons. The quantum vacuum is teeming with invisible activity, with hidden fluctuations that can't be directly observed, but that constantly influence everything that can be. Now here is where the quantum vacuum connects to the biggest mystery in cosmology. When physicists try to calculate the energy density of the quantum vacuum, the amount of energy contained in a given volume of empty space due to these virtual fluctuations, they get a number, a specific calculable number based on quantum field theory. And when they compare this calculated number to the observed energy density of dark energy, the actual measured energy of the vacuum of space that is driving the accelerating expansion of the universe, they find a discrepancy, not a small discrepancy, the largest discrepancy in the history of physics. The theoretical prediction is roughly 10 to the power of 120 times larger than the observed value. That is a 1 followed by 120 zeros. The prediction is off by a factor of 10^120. This is sometimes called the worst prediction in the history of science, not as an insult to the physicists involved, but as an honest acknowledgement of just how spectacularly the most fundamental theory of matter fails to describe the actual energy of the vacuum. Something is canceling out most of that vacuum energy. Something is suppressing it to almost exactly zero, but not quite exactly zero, leaving just enough to drive cosmic acceleration. We don't know what that something is. This is called the cosmological constant problem, and it is one of the most profound unsolved problems in all of physics. The energy of empty space, the energy of nothing, is hidden from our best theories by a factor of 10^120. At this point, you might find yourself doing something interesting, something that happens when a large enough number of strange things accumulate in one place. You might find yourself stepping back and asking, not just about each individual mystery, but about the fact of the mysteries themselves. Why are there so many? Why do they cluster around the same theme? Invisibility, hiddenness, inaccessibility. Why does every scale of the universe, the cosmic, the galactic, the quantum, the informational, have its own version of the same story. Something is here that you cannot see. Something exists that you cannot measure. Something is happening that your best theories cannot fully describe. This clustering of mysteries is not random. In science, when you find the same pattern appearing in multiple independent domains, it is a signal. It means the pattern is pointing toward something real. And the pattern here, the consistent, recurring, almost systematic hiddenness of reality, is pointing toward a possibility that is at once deeply scientific and deeply strange. The possibility that the universe, as we perceive it, is not a complete description of reality. That our perception, and perhaps even our capacity for perception, is fundamentally limited in ways that are not merely technological but structural. That we are inside a reality that is, by design or by nature, only partially transparent. Think about the concept of an event horizon. An event horizon is the boundary around a black hole beyond which nothing can escape. Inside the horizon, space-time is so severely curved by the black hole's gravity that all possible future paths lead inward, toward the singularity. There is no trajectory that leads out, not for matter, not for light, not for any signal of any kind. The inside of a black hole is causally disconnected from the outside. Nothing that happens inside can ever communicate with anything outside. The information is trapped. The events are hidden. For an observer outside the black hole, the interior is permanently, absolutely inaccessible. You will never know what's inside. You can calculate, you can infer, you can model, but you will never receive direct information from inside the horizon. And now consider, the cosmological horizon of the observable universe is, mathematically, remarkably similar to an event horizon. Regions beyond our cosmic horizon are causally disconnected from us. Events beyond the horizon cannot send signals that reach us. Information from beyond the horizon is permanently inaccessible. We live inside a cosmic event horizon, a bubble of causally connected space, surrounded on all sides by a boundary beyond which reality continues but communication is impossible. We are inside a black hole of information. The universe has given us a window, a large, beautiful, extraordinary window, but it has placed that window inside an event horizon, and outside the horizon, reality continues without us. The event horizon of the observable universe is not a physical wall. You could travel toward it, and as you approach, the cosmic horizon would retreat, because it is not a fixed location in space. It is a boundary defined by the speed of light relative to cosmic expansion, but you would never escape it. No matter how far you traveled, you would still be inside your own observable universe, your own bubble of causality, with a new horizon surrounding you. You cannot break out. You cannot see what's beyond. You are always inside, always observing from within a finite bubble of accessibility, surrounded by an infinity of inaccessibility. The universe is not showing you everything. It has given you a theater, and it has drawn curtains on everything outside the theater, and the curtains are made of physics itself, made of the speed of light and the age of the universe and the acceleration of expansion, and no instrument, no experiment, no act of human ingenuity will ever part those curtains. They are drawn by the structure of space-time. The hidden part of reality is hidden not by accident, not by technological limitation, but by the architecture of the cosmos. Now consider what it means to be an observer inside this architecture. You are not a neutral external measurer of the universe. You are inside it. You are made of it. You are, in a quite literal sense, a configuration of the universe that has become complex enough to observe itself. And the question of what an observer embedded in a system can know about that system is a deep and fascinating question in philosophy, in information theory, in physics. Gödel's incompleteness theorems, the mathematical results proved by Kurt Gödel in 1931, established that within any sufficiently complex formal system, there are true statements that cannot be proved within the system. There are truths that are real but inaccessible from inside the system's own framework. This is a mathematical result, not a physical one, but its resonance with the physical situation is hard to ignore. If the universe is, at some level, a formal system, a set of rules and initial conditions evolving according to those rules, then Gödel's theorems suggest that there will be truths about that system that cannot be derived from within it. Truths that exist, but that are inaccessible to any mind that is itself part of the system. And every mind we know about is part of the universe. Every observer is inside the system. Every measurement, every calculation, every scientific theory is produced by minds that are themselves made of the universe's matter, running on the universe's physics, embedded in the universe's space-time. We are the universe trying to understand itself, And Gödel suggests that any system trying to understand itself will always encounter limits, truths that are real, but that the system cannot access from within. This is not defeatism. It is not an argument for giving up on science or for abandoning the pursuit of understanding. It is something subtler and more interesting. It is an argument that the universe has a depth that cannot be fully plumbed from the inside. That reality has layers below the layer we inhabit, and those layers may never be directly accessible to any observer who is part of the layer above. We can see the effects, we can measure the shadows, we can infer the shapes of things we cannot directly observe. But the things themselves, the deep structures, the hidden substrates, the fundamental ingredients of reality that express themselves in dark matter and quantum uncertainty, and black hole information and vacuum energy, remain behind a veil that is not made of ignorance but made of structure. Let's talk about the simulation hypothesis, not because it is certainly true, it is not, and it may not even be testable in any rigorous sense, but because it represents the logical endpoint of the hidden universe theme, the place where all the threads converge into a single haunting possibility. The simulation hypothesis, associated most prominently with philosopher Nick Bostrom, and more recently with physicist Silas Bean and others, proposes that the universe we inhabit might be a computational simulation, a program running on some substrate outside our universe, generating the appearance of physical reality for observers inside. The hypothesis begins with a simple observation. If it is possible to create sufficiently detailed simulations of conscious observers, then over time, simulated observers would vastly outnumber non-simulated ones. Which means that if we assign equal prior probabilities to being simulated or not, the odds favor simulation. This is the probabilistic argument, but the more interesting version of the hypothesis is the physical one. Several physicists have pointed out that the laws of nature as we understand them have a strikingly computational character. Quantum mechanics is discrete. Energy comes in quantized packets, not continuous streams. Space itself may be quantized at the Planck scale, the smallest possible length, below which the concept of distance may lose meaning. The fabric of space becoming something grainy and digital, like the pixels of an image viewed from too close. The speed of light is not just fast, it is a universal speed limit, the maximum rate of information transfer, the kind of constraint you would expect to find in a computational system with a finite processing speed. The laws of physics are describable as algorithms, step-by-step procedures that take an initial state and evolve it forward in time. Physicists have found that certain calculations in quantum field theory can be performed most efficiently using computational techniques that look remarkably like Monte Carlo simulations, the same kind of random sampling used in computer simulations of complex systems. None of this proves simulation, but it suggests that the universe has properties consistent with a computational process. And a computational process has a substrate, hardware, code, and architecture that exists outside the program itself. If the universe is computational, then the substrate on which it runs is permanently hidden from inside the computation. You are inside the program. The code is invisible to you. There's an extraordinary experiment that has been proposed, and in limited forms partially attempted, to test whether the universe has the discrete, pixelated structure you would expect if it were running on a computational substrate. If space is quantized at the Planck scale, then very high-energy cosmic rays, particles traveling across the universe at nearly the speed of light, should show a particular kind of distortion when they arrive at Earth, because the discrete structure of space would affect the way their polarization changes over their long journey. The Fermi Gamma Ray Space Telescope has looked for this distortion in gamma rays from distant gamma ray bursts, and the results are interesting. The measurements are consistent with space being smooth, not pixelated, down to scales far below the Planck length, which either means the universe is not computational at this level, or our model of what computational space looks like is wrong, or the test is not the right one. The universe characteristically has not given a clean answer. It has given data that is consistent with multiple interpretations and declined to choose between them. But perhaps the most striking thing about the simulation hypothesis, the reason it keeps coming back into scientific and philosophical discussion despite being largely untestable, is not its conclusion, but its premise. The premise is that the universe as we experience it is not the fundamental level of reality, that there is something beneath it, something more basic, something that generates our universe the way a program generates a game world. And this premise, in that there is a deeper layer, that what we see is not the bottom, is not unique to simulation theory. It is shared in different forms by string theory, by the holographic principle, by quantum gravity, by digital physics, by every framework physicists have constructed to go deeper than the standard model. They all say the same thing. What you see is not the bottom. There is more below. The floor is not where you think it is. The universe has a basement, and the door is locked from the outside. The question of hidden dimensions brings us to one of the most extraordinary experimental endeavors in human history, the Large Hadron Collider at CERN, the particle accelerator buried beneath the border of France and Switzerland, where protons are accelerated to within a fraction of a percent of the speed of light and smashed together with energy sufficient to recreate conditions from the earliest moments after the Big Bang. The LHC was built partly to find the Higgs boson, the particle associated with the field that gives other particles their mass, and in 2012, it did exactly that, confirming the last missing piece of the standard model of particle physics. That was a triumph. But the LHC was also expected to find something beyond the standard model. Supersymmetry, the theory that every known particle has a heavier super partner, was expected to reveal itself at LHC energies. Extra dimensions were expected to leave signatures in the collision data. New physics, whatever form it took, was expected to show up. It hasn't. After years of operation and trillions of collision events, the LHC has found the Higgs boson and nothing else that wasn't already predicted. The data is consistent with the standard model and only the standard model. No supersymmetric particles, no evidence of extra dimensions, no new forces, no new particles, no physics beyond the already known. This absence is itself extraordinary. The absence is data. The fact that the LHC found nothing beyond the standard model at the energies it can reach tells us that whatever lies beyond the standard model, whatever explains dark matter, whatever resolves the hierarchy problem, whatever connects quantum mechanics and general relativity, is hidden at energies higher than the LHC can achieve. The new physics exists. It must exist because the standard model is demonstrably incomplete, but it is hiding beyond the reach of the most powerful particle accelerator ever built by human civilization. The universe has drawn another veil. This one is not made of distance or horizon or quantum uncertainty. It is made of energy. To see what lies beyond the standard model, you need energy scales that no human technology can currently reach. Scales near the Planck energy, which is about 10-19 times the mass energy of a proton, roughly 10-15 times beyond the reach of the LHC. The gap between where we can look and where the answers might live is not merely large. It is, by any practical measure, nearly infinite. We are like archaeologists who have dug down 1 centimeter into a site that goes down to the center of the Earth. And yet, and this is the strange, almost beautiful thing about the situation, even though the new physics is hiding beyond our experimental reach, we can infer its existence from the physics we can see. The standard model is not just incomplete. It is demonstrably, structurally incomplete in ways that point toward specific kinds of missing physics. The hierarchy problem, the question of why the Higgs boson is so much lighter than the Planck mass, when quantum corrections should drive its mass up to the Planck scale, screams that there is something canceling those corrections, some deeper structure, some symmetry or mechanism operating at a hidden scale. The fact that the 3 forces of the standard model, electromagnetism, the weak force and the strong force, almost but don't quite unify at high energies, suggests there's a missing piece in the grand unified picture. The fact that we have 3 generations of quarks and leptons, 3 copies of the particle families with no known reason for exactly 3, suggests a pattern whose explanation lives at a scale we can't yet access. The standard model is like a photograph of a person that only shows them from the shoulders up. You can see enough to know there's more. The rest is hidden below the frame. Now let's turn to something even more personal, something that brings the hidden universe theme directly to the question of perception, of how you, right now, are experiencing reality. Your brain is a biological organ that evolved over hundreds of millions of years not to perceive reality accurately, but to perceive it usefully. These are not the same thing. Evolution does not reward truth-telling. It rewards survival. And for a biological organism trying to survive in a complex environment, a simplified, compressed, utility-optimized representation of reality is far more useful than an accurate, complete, unfiltered one. Your visual system, for example, does not give you a photograph of what's in front of you. It constructs a representation, a model, based on a relatively small amount of incoming light information, filled in with predictions, compressed in ways that emphasize motion and contrast and familiar patterns, filtered to discard information that doesn't seem relevant, interpreted through a framework built from past experience. You do not see the world. You see your brain's best guess about the world, rendered in real time, updated continuously, but always and necessarily a reconstruction rather than a recording. This is not a metaphor. Neuroscience has documented the ways in which your perceptual system constructs reality rather than simply recording it. Optical illusions work because your visual system applies rules about lighting, perspective, and context that produce incorrect interpretations when those rules are applied in unusual situations. The existence of optical illusions is not evidence that your visual system is broken. It is evidence that your visual system is doing something. It is applying a model, and the model can be fooled, which means the model is a model, not a direct readout of reality. Change blindness. The well-documented phenomenon where people fail to notice large, obvious changes to a visual scene when their attention is directed elsewhere, shows that you don't see everything in front of you. You see what you're focused on, what your attention selects, what your cognitive system flags as relevant. The rest goes unseen, not because it isn't there, but because your brain, economizing ruthlessly, doesn't construct a representation of it. You live in a selective window onto reality. Everything outside that window exists. You simply don't see it. And now consider, if the human perceptual system is a filter, if it shows you not reality, but a compressed, selective, utility-optimized model of reality, then the question of what that filter is designed to pass and what it is designed to block becomes deeply important. Evolution built your senses for the middle world, the world of objects and organisms at human scales, moving at human speeds, existing at human temperatures. Your eyes are sensitive to a narrow band of electromagnetic radiation, visible light, that is useful for navigating a surface environment. You cannot see infrared, radio waves, X-rays, or gamma rays without instruments. You cannot perceive magnetic fields, electrical fields, or gravitational waves without instruments. You cannot directly sense quantum phenomena or dark matter or the curvature of space-time. All of these things are real. All of them are present. All of them are happening around you and through you right now. But you evolved to see none of them, because none of them were useful for the immediate practical task of surviving on the surface of a medium-sized planet. Your perceptual system is a survival tool, not a truth detection system. And because of this, the reality you experience and the world you perceive and navigate and live in is a tiny slice of the reality that actually exists. Physicist Donald Hoffman has taken this argument further than most, developing what he calls the interface theory of perception. The idea that our perceptions are not approximations of reality, but are instead interfaces with reality, the way a computer desktop is an interface with the underlying code. You don't see the zeros and ones when you move an icon on a screen. You see the icon. The icon is useful. It allows you to interact with the underlying code effectively, but it bears no resemblance to that code. The icon is real in the sense that it exists and functions and allows you to accomplish things, but it is not deep reality. It is a surface. Hoffman argues that evolution has given us a perceptual interface that is tuned for fitness, for survival and reproduction, and that this interface may bear no more resemblance to underlying reality than a desktop icon bears to transistor operations. We are, by this account, not perceiving reality. We are navigating an interface designed by natural selection, interacting with a reality that lies permanently beneath the surface of what we can perceive. If Hoffman is right, and he has formal mathematical models supporting his view, though it remains controversial, then the hiddenness of reality is not just a problem in physics. It is not just dark matter and quantum mechanics and cosmic horizons. It is a problem in perception itself. The deepest layer of the universe's opacity may not be out there in the cosmos, measured in light years and giga-electron volts. It may be here immediately in the gap between the world as your brain renders it and the world as it actually is. The hidden universe is not only the universe beyond telescopes. It is the universe beyond your eyes, beyond your neurons, beyond the perceptual model your brain constructs every moment of your waking life. The filter is not between you and the far cosmos. The filter is between you and everything. And here something extraordinarily interesting happens, because when you take the theme of the hidden universe seriously, when you follow it from dark matter and cosmic horizons down through quantum mechanics and holographic principles and into the structure of perception itself, you arrive at a place that science and philosophy have been circling for centuries without quite landing on it directly. You arrive at the question of consciousness. Not consciousness as a psychological phenomenon, not consciousness as something to be studied in the third person by neuroscientists measuring brain activity, but consciousness as a fundamental question about the relationship between an observer and the reality it observes. The hard problem of consciousness, why there is subjective experience at all, why the physical processes of the brain give rise to something it is like to be a person, is perhaps the most profound unsolved problem not just in neuroscience, but in all of human inquiry. And it is intimately connected to the hidden universe theme, because the hard problem is essentially a problem about hiddenness. Your subjective experience, the redness of red, the pain of pain, the feeling of understanding, is real, undeniably real, the most immediately real thing you have access to, and yet it is completely invisible to any third-person description of your brain. Neuroscience can describe the neurons firing. It can map the correlates of consciousness. It cannot explain why those correlates give rise to experience. The experience itself, the felt quality of being, is hidden from the outside observer. You are hidden from outside observers, and outside observers are, in some deep sense, hidden from you. The connection between consciousness and the hidden structure of the universe is not merely philosophical. It has a precise physical formulation in what's called the quantum Zeno effect, and more broadly in the role of the observer in quantum mechanics. If consciousness is what collapses the wave function, if subjective experience is what converts quantum possibility into classical actuality, then consciousness is not merely a product of the physical universe, a phenomenon that emerges from matter. It is a participant in the physical universe, a process that actively shapes what becomes real. This is a minority position in physics associated with the so-called Copenhagen interpretation in some readings, and with more radical proposals by physicists like Eugene Wigner and later John von Neumann. It has never achieved consensus and faces serious objections, but the problem it points toward, the role of the observer in quantum mechanics, the relationship between consciousness and physical reality, has never been resolved, and its unresolved nature is itself part of the pattern. The observer is part of the measurement. The observer is not standing outside the universe looking in. The observer is inside. The observer is made of the same stuff being observed, and this creates a circularity, consciousness arising from matter, matter only becoming definite through observation, observation arising from consciousness, that has no clean resolution. It is a knot at the center of our understanding of reality, and we have been unable to untie it for a century. Let's step into territory that is even more speculative, but deeply fascinating. The question of whether the universe's hiddenness might be informative in a different sense, not just as a collection of things we don't know, but as a positive signal about the structure of reality. In information theory, a message has a sender and a receiver. The message can be encoded, hidden in a sense, in a way that requires a key to decode. The existence of encoding implies structure, the structure of the code, and the existence of a code implies that the universe at some level is organized informationally rather than merely physically. Physicists John Wheeler coined the phrase "it from bit," the idea that physical reality emerges from information, that every physical quantity, every it, derives its existence from answers to yes or no questions, from bits. This is a radical proposal, that the universe is not fundamentally made of matter or energy or fields, but of information. That reality is informational at its core, and matter and energy are emergent properties, the way temperature is an emergent property of molecular motion, or the way a wave is an emergent property of water. If this is correct, then the hidden layers of the universe are not hidden physical things, they are hidden information. They are bits we haven't found the decoder ring for yet. This informational view of reality has gained significant traction in recent years, particularly in the context of quantum information theory and quantum gravity. The realization that quantum entanglement, the phenomenon whereby two particles can share a quantum state, such that measuring one instantly determines something about the other, regardless of the distance between them, might be the fundamental thread from which the fabric of space-time is woven, is one of the most striking recent developments in theoretical physics. The idea, associated with the work of Mark van Ramsdonk and developed through the Doreen-EPR conjecture by Maldacena and Susskind, is that the connectivity of space-time, the way different regions of space are geometrically related to each other, might emerge from quantum entanglement. Connected regions of space-time correspond to entangled quantum systems. Disconnect the entanglement, and the space-time tears apart. In this picture, space itself is not a backdrop against which things happen. It is a structure that emerges from the quantum informational relationships between the things. The geometry of the universe is a consequence of the entanglement structure of its quantum fields. Space is woven from invisible threads of quantum correlation. Invisible not because they're hidden from your instruments, but because they exist at a level of description that is more fundamental than space itself. If space emerges from entanglement, then asking what lies beneath space, asking about the structure of reality at a level more fundamental than space-time, requires thinking in terms of quantum information rather than in terms of geometry. The deeper layer is not spatial. It cannot be mapped, it cannot be located. It is a web of correlations, a network of quantum relationships, a structure that gives rise to the appearance of space and time the way pixels give rise to the appearance of a landscape on a screen. And the pixels, in this analogy, are not physical objects you could go and look at if only you had a good enough microscope. They are informational entities, bits, qubits, quantum correlations, that exist at a level of description that is prior to the physical. They are not in space. Space is made of them, and this means that the deepest hidden layer of the universe is not hidden in space. It is hidden beneath space. It is hidden at a level of reality that our entire conceptual framework, built on the assumption of space and time as given, is not equipped to access. We talk about the speed of light as a fundamental constant of nature, a universal speed limit that nothing with mass can exceed. And this is true, experimentally verified and incorporated into every accurate theory of physics. But the way physicists understand the speed of light has a depth to it that the simple, nothing goes faster version doesn't capture. The speed of light is not merely a speed. It is the conversion factor between space and time in the structure of spacetime. It is what links the spatial dimensions to the temporal dimension in Einstein's four-dimensional spacetime. Without the speed of light as a conversion factor, the geometry of spacetime, the way distances in space and intervals in time are related, would be meaningless. The speed of light is the rate at which the geometry of reality operates. It is the clock speed of the universe. And because information can only travel at the speed of light or slower, the speed of light is also the maximum rate at which any part of the universe can be informed of anything happening elsewhere. It is the universe's bandwidth, and the universe's bandwidth is finite. The cosmos cannot communicate with itself faster than light. It cannot be fully self-aware. Different regions of the universe are processing their local physics without full knowledge of what is happening elsewhere. The universe is, in this sense, not only hidden from you, it is partially hidden from itself. Consider what this means in the context of the early universe. In the first moments after the Big Bang, the universe was much smaller than it is now, and regions that would later become separated by billions of light years were close enough to communicate, close enough that their physics could influence each other, could equilibrate, could reach a common temperature and density. This period of communication is called the period of causal contact. As the universe expanded, regions that were once in causal contact lost touch with each other. The expansion carried them beyond each other's light travel distance, making communication impossible. The large-scale uniformity of the universe, the fact that the cosmic microwave background has the same temperature to roughly 1 part in 100,000 across the entire sky, even between regions that have been causally disconnected since a fraction of a second after the Big Bang, is one of the deepest mysteries of cosmology. Why are they the same temperature if they haven't been able to communicate? Inflation theory, the proposal that the universe underwent an extremely rapid period of exponential expansion in the first fractions of a second, is the most widely accepted explanation. Before inflation, all these regions were in causal contact and equilibrated. Inflation then stretched the universe so rapidly that the regions that had equilibrated were pushed far beyond each other's horizons. The uniformity we see is a record of a time when the universe was small enough to talk to itself, before expansion hid most of it from most of the rest. The universe once knew more about itself than it does now. Expansion has been taking that self-knowledge away. The universe is becoming more hidden to itself over time. Inflation itself, the theory invoked to explain the uniformity of the CMB and the flatness of the universe and the origin of structure, is another layer of hidden reality. We have never directly observed inflation. We cannot directly test it. We infer it from its predictions. The flatness of the universe, the scale invariant spectrum of CMB fluctuations, the suppression of spatial curvature, all of which match observations remarkably well. But the mechanism of inflation, the identity of the inflaton field that drove it, the physics of what happened before inflation, the question of what started inflation and what stopped it, all of this remains deeply uncertain. shrouded in the opacity of an era we cannot directly access. Inflation happened, if it happened, at energy scales far beyond anything we can probe experimentally. The inflaton field, the hypothetical scalar field whose energy drove the exponential expansion, has never been detected. We don't know what it is. We don't know if it still exists in some form today. We don't know if inflation was a single event or part of a recurring process. We have a story about the first fraction of a second of the universe's existence, a story that matches the evidence remarkably well, and yet the main character of that story, the inflaton, remains invisible, unidentified, a ghost in the cosmological machine whose presence we infer entirely from the footprints it left behind in the structure of the cosmos. And inflation brings us to one of the most mind-expanding and deeply unsettling ideas in all of modern cosmology: eternal inflation and the multiverse. Most versions of inflation predict that once inflation starts, it doesn't stop everywhere at once. Different regions of space stop inflating at different times, forming what physicists call bubble universes, regions of space where inflation has ended and normal physics has begun, surrounded by a still inflating background that continues to expand exponentially forever. Our universe is, in this picture, one bubble among an infinite number of bubbles, each nucleating out of the inflating background at different times, each potentially with different physical constants, different values of the speed of light, different masses for elementary particles, different strengths of the fundamental forces. The multiverse of eternal inflation is a landscape of universes, each real, each governed by physics, but each separated from all others by an inflating void that expands faster than light and cannot be crossed. The other bubbles are not just far away, they are causally inaccessible, permanently, absolutely by the structure of physics itself. If the multiverse is real, then our universe is not the universe. It is a universe, one of an infinite number, and all the others are hidden from us in a way that makes the 95% of dark matter and dark energy seem like a minor concealment. The multiverse is not the hidden part of our universe. It is the hidden part of reality that contains our universe. We are a bubble in a sea of bubbles, and the sea is invisible by necessity. The multiverse is controversial, and it should be. In its current form, it makes no unique testable predictions that distinguish it from a single universe cosmology. And some physicists argue that a theory which cannot be tested is not science but metaphysics. This is a legitimate concern, but the multiverse is not generated by idle speculation. It is a prediction that falls directly out of the mathematics of inflation, mathematics that was developed for independent reasons and that has passed observational tests in its domain of applicability. The multiverse is an uncomfortable conclusion reached by following the physics where it leads. And whether you accept the multiverse as a genuine physical reality or regard it as an artifact of our models, its existence as a serious scientific concept points to the same thing. The universe we can observe may be embedded in a context, a larger structure, a higher frame, that is permanently beyond our observational reach. We are inside a picture that may be part of a gallery we will never see. The frame of our observable universe may be just one frame among an infinite number, hung in a space so vast and so disconnected from ours that its existence makes no detectable difference to anything inside our bubble. The hiddenness in this case is not just structural, it is absolute. Let's return to something more immediate and more precise, something happening right now in laboratories and observatories around the world that is deepening the mystery rather than resolving it. In recent years, a series of experiments and observations have produced results that don't fit neatly into any existing theoretical framework. The muon anomalous magnetic moment experiment at Fermilab, known as muon G2, has measured the magnetic properties of muons with extraordinary precision and found a value that differs from the standard model prediction by an amount too large to be explained by measurement error. The muon is behaving differently than it should. Something is interacting with it, some quantum field, some particle, some effect, that the standard model does not include. We don't know what it is. We know something is there because the muon is telling us so, but what it is and what its deeper implications are remain hidden. Similarly, the LHCb experiment at CERN has accumulated data on the decays of B mesons, particles containing bottom quarks, and found patterns of decay that are subtly but significantly inconsistent with standard model predictions, suggesting that the forces governing these decays are not quite what we think they are. Taken individually, each of these anomalies might be explained away. Taken together, alongside the Hubble tension, alongside the flat rotation curves, alongside the vacuum energy problem, they form a chorus of whispers, each saying the same thing in a slightly different voice. There is more here than you can see. The whispers have been getting louder. In 2023 and 2024, the Pulsar Timing Array collaborations, groups of astronomers using networks of rapidly rotating neutron stars as precise cosmic clocks, announced the detection of a gravitational wave background. Not a single gravitational wave event, like the black hole mergers detected by LIGO, but a background hum of gravitational waves permeating all of space, a low-frequency ripple in the fabric of space-time that seems to be everywhere at once. The likely source of this background is supermassive black hole binaries, pairs of enormous black holes, each billions of times the mass of the Sun, slowly spiraling toward each other at the centers of merging galaxies across the universe, emitting gravitational waves as they do so. The detection is extraordinary. It opens a new window onto the cosmos, a new way of seeing that doesn't rely on electromagnetic radiation at all. Gravitational wave astronomy is, in a very literal sense, a new way of perceiving the universe that bypasses the limitation of light entirely. And what it is beginning to show us is a universe that was hidden in plain sight, a universe full of dynamic, massive, violent processes that left no electromagnetic trace, but were writing their history in the geometry of space-time all along. The universe has been speaking in gravitational waves for billions of years. We have only just developed the ears to hear it. And what will we find as gravitational wave astronomy matures? What will we hear when we build the next generation of instruments? LISA, the space-based gravitational wave observatory planned for the 2030s, sensitive to lower frequencies than ground-based detectors, capable of seeing gravitational waves from supermassive black hole mergers across the entire observable universe, from white dwarf binaries in our own galaxy, from the primordial gravitational wave background generated in the first moments of the Big Bang. We will hear things that have been happening for billions of years in complete silence. Silence to our electromagnetic senses. Silence to every instrument we have built up to now. The universe has an acoustic history that we have been deaf to since the beginning of our existence. The gravitational wave background is the universe's music played on space-time itself. And we are only now, at this moment in the history of science, beginning to press our ears to the ground and hear the first notes. What the full symphony will reveal, what hidden events, what hidden structures, what hidden physics the gravitational sky will show us, is a question that cannot yet be answered. We are at the beginning of a new kind of seeing. And every new kind of seeing has historically revealed not just new objects but entirely new categories of phenomenon, entire new domains of reality that were invisible before the new instrument existed. We don't know what the gravitational universe will show us. That is the most exciting and most unsettling thing that could be said. There is a concept in physics called spontaneous symmetry breaking that is worth understanding deeply because it captures something essential about the relationship between hidden structure and observable reality. A symmetry, in physics, is a transformation that leaves something unchanged. If you rotate a perfect sphere, it looks the same. The sphere has rotational symmetry. Many of the fundamental laws of physics have symmetries. They look the same if you translate in space or in time, or if you exchange certain kinds of particles. But the universe we observe does not always reflect these symmetries. The laws are symmetric, but the state of the universe is not. When a symmetry that is present in the laws is absent from the state of the universe, we say the symmetry has been spontaneously broken. The most familiar example is a magnet. The laws governing the atoms in a magnet are perfectly symmetric. There is no preferred direction built into the physics, but below a certain temperature, the magnet spontaneously picks a direction and all its atoms align. The symmetry of the law is broken by the state of the system. The direction the magnet chose is not contained in the law. It was determined by chance, by initial conditions, by quantum fluctuations. The underlying symmetry is hidden beneath the asymmetric state. Spontaneous symmetry breaking is everywhere in physics. The Higgs mechanism, the process by which elementary particles acquire mass, is a form of spontaneous symmetry breaking. The electroweak force, which is a unified description of electromagnetism, and the weak nuclear force is symmetric at high energies. They are the same force at the energies of the early universe. At lower energies, the symmetry is broken, and what we observe are two distinct forces: electromagnetism, which is long-ranged and described by massless photons, and the weak force, which is short-ranged and described by very heavy W and Z bosons. The difference between these two forces, the difference between the force that makes your phone work and the force that causes radioactive decay, is a consequence of hidden symmetry. There is a deeper unity beneath the apparent difference, a symmetry that exists at a level we can only reach at high energies, a more fundamental layer of reality that the broken, low-energy world we inhabit conceals. We live in a broken symmetry state. The more fundamental, more symmetric reality lies beneath the visible surface, accessible only at energies and temperatures that no longer exist naturally in the universe, energies that existed only in the first moments after the Big Bang, in conditions that are gone forever. This means that the universe as it is now, cold, dilute, with its forces separated and its symmetries broken, is a less fundamental state than the universe as it was in its earliest moments. The deep reality, the high symmetry, high energy state where the fundamental forces unify and the hidden structures become visible, existed at a temperature and energy that no longer exists anywhere in the natural universe and can only be approximated briefly and locally in particle accelerators. The universe has cooled away from its own fundamental nature. It has settled into a low energy state where the symmetries are broken and the deep structure is hidden. The universe has hidden its own foundations behind the veil of its own cooling. To see the true underlying structure of physics, the unified, symmetric, fundamental layer from which all the forces and particles emerge, you would need to recreate conditions that last existed a fraction of a second after the Big Bang. And even the LHC, humanity's most powerful instrument for recreating those conditions, falls enormously short of the energies required. The universe has cooled its deep nature into invisibility. The fundamental reality froze behind a phase transition, and all we can see is the broken, crystallized surface. Think about ice. When water freezes, it transitions from a state in which water molecules are free to move in any direction, a high symmetry state, to a state in which they are locked into a crystal lattice, pointing in specific directions, with specific neighbors, with a specific structure. The ice crystal is less symmetric than the liquid. The freedom of the liquid has been replaced by the ordered, constrained structure of the solid. But the ice crystal has new properties that the liquid didn't have. It has a structure, a pattern, a geometry. The breaking of symmetry created something new. Physics says that the universe underwent a series of phase transitions in its early history, transitions analogous to water freezing, in which symmetries were broken and new structures emerged. And each of these transitions hid a deeper layer of symmetry beneath the surface of the new broken state. The universe as it exists now is like a landscape of ice, apparently solid, apparently final, apparently complete. But beneath the ice is the water that was there before it froze. Beneath the water is the steam that was there before it condensed. Beneath the steam are the fundamental fields in their fully symmetric, unbroken state. Each layer is hidden beneath the one above. We live on the surface of the most broken, most crystallized, most cooled down layer, the furthest from the fundamental. We are living on top of the most hidden version of reality. There is something profound in the fact that as the universe evolved, as it cooled and expanded and grew more complex, its fundamental nature became progressively more hidden. In the very first moments after the Big Bang, when the universe was unimaginably hot and dense, all the forces were unified, all the symmetries were intact, and the universe was as transparent to itself as it could be. Every particle in causal contact with every other particle, every force operating at the same scale, every hidden symmetry expressed and visible. Then the cooling began. The symmetries broke. The forces separated. Structures formed. Quarks bound into protons. Protons and electrons combined into atoms. Atoms clumped into stars and galaxies. Complexity emerged, and with complexity came opacity. The universe built layers upon layers, particles, atoms, molecules, cells, brains, civilizations, and each layer emerged from the one beneath it in ways that are not fully reducible to the simpler layer. Each layer has its own logic, its own patterns, its own laws, and each layer partially hides the one beneath it. You are a layer. Your experience of the universe is filtered through every layer between you and the quantum fields at the bottom. You are standing at the top of an enormous stack of emergent complexity, looking outward at a universe that is doing the same thing, layering, emerging, hiding its own foundations beneath the structures it builds. Emergence is one of the most fascinating and least understood phenomena in all of science. When you combine large numbers of simple things following simple rules, you sometimes get behaviors and properties at the collective level that are completely absent from and completely unpredictable by the simple level. Water molecules are not wet. No single water molecule is wet. But combine enough of them and wetness emerges, a genuine property of the collective that has no analog at the individual level. Neurons are not conscious. No single neuron thinks. But combine enough of them in the right architecture and consciousness emerges, or at least something that correlates with consciousness emerges. The laws of thermodynamics, temperature, pressure, entropy, emerge from the statistical behavior of large numbers of particles, even though the microscopic laws governing each individual particle contain nothing that looks like temperature or pressure or entropy. Emergence means that reality is not simply the sum of its parts. It means that new properties, new behaviors, new laws appear at higher levels of organization that are not present at lower levels. And this means that the higher levels, the emergent layers, are, in a genuine sense, hiding the lower layers. You cannot directly read the neural code from the thought. You cannot directly read the molecular structure from the wetness. The emergent property conceals its origin in the same act by which it creates itself. The concept of emergence has radical implications for the hidden universe theme, because it suggests that the universe's hiddenness is not just a matter of scale, not just a matter of things being too big or too small or too far or too fast for our instruments to measure. It is a matter of levels. Reality is organized in levels, and the relationships between levels are complex, non-linear, and frequently such that the higher level cannot be fully derived from or reduced to the lower level. Consciousness cannot be fully derived from neuroscience. Biology cannot be fully reduced to chemistry. Chemistry cannot be fully reduced to physics, at least not practically, because the complexity of a biological molecule is so great that computing its behavior from first principles is beyond any existing or foreseeable computational system. The higher levels are hidden from the lower levels in one direction, and the lower levels are hidden from the higher levels in another direction. The universe hides itself from itself at every transition between levels, and you, as an observer, are operating at one of these levels, the level of biological cognition and perception, which means that levels both above and below yours are, to varying degrees, hidden from you. There is a particular kind of scientific result that is more unsettling than a simple anomaly, more unsettling even than a clear discrepancy between theory and observation. It is the kind of result where the closer you look, the more complex and strange the picture becomes, where precision increases the mystery rather than diminishing it. The fine structure constant is one such result. The fine structure constant, denoted by the Greek letter alpha, is a dimensionless number, approximately 1/137, that characterizes the strength of the electromagnetic force. It is one of the fundamental constants of nature, and it appears throughout physics in the calculation of every electromagnetic process. Richard Feynman called it one of the greatest damn mysteries of physics, a magic number that came to us with no understanding by man. We can measure it with extraordinary precision. It is perhaps the most precisely measured quantity in all of science, known to more than 10 decimal places, but we cannot derive it. We cannot explain why it has the value it has. It is a pure number with no apparent reason for being that particular number rather than any other. It could, as far as we can tell, have been different, a slightly different value, and atoms would not form, stars would not burn, chemistry would not exist, life would be impossible. The fine structure constant is tuned to a value that permits complexity and life, and we don't know why. It is as if the universe was set up with a specific value inserted for a specific reason, but the reason itself is hidden. This fine-tuning, the observation that the fundamental constants of nature appear to be adjusted with extraordinary precision to permit the existence of complexity, chemistry, and life, is known as the anthropic coincidence, and it is one of the deepest and most divisive topics in modern physics. The constants don't just permit life, they are precisely calibrated to permit it, in ways that seem implausibly specific if the constants were chosen randomly. If the strong nuclear force were slightly weaker, atomic nuclei would not hold together, and there would be no atoms. If it were slightly stronger, hydrogen would fuse to helium in the early universe so efficiently that there would be no hydrogen left, and no water, no organic chemistry, no life. If dark energy were slightly stronger, even a tiny fraction stronger, the universe would have expanded too rapidly for matter to clump into galaxies and stars. If it were slightly weaker, the universe would have collapsed back on itself long ago. The constants are not just compatible with life, they are exquisitely tuned for it. And the question of why they are tuned this way, whether it is coincidence, necessity, design, or the result of a multiverse in which all possible values are realized somewhere, and we inevitably find ourselves in a region where life is possible, is a question that physics cannot currently answer. The reason for the fine-tuning is hidden. The origin of the constants is hidden. The deeper principle, if there is one, that fixes the values of the fundamental constants of nature is one of the deepest hidden things in the universe. There is a version of the fine-tuning argument that goes even deeper and is even stranger. It is the argument from mathematics. Eugene Wigner, in a famous 1960 essay, wrote about the unreasonable effectiveness of mathematics in the natural sciences, the puzzling fact that abstract mathematics, developed by pure mathematicians for purely aesthetic and logical reasons, with no concern for physical application, repeatedly turns out to describe physical reality with extraordinary precision. Non-Euclidean geometry, developed by 19th century mathematicians exploring the logical consequences of changing the parallel postulate with no intention of describing anything physical, turned out to be exactly the mathematics Einstein needed to formulate general relativity, the theory of gravity that describes the large-scale structure of the universe. Group theory, an abstract branch of algebra developed to classify mathematical symmetries, turned out to be the exact language needed to describe the symmetries of elementary particles and the structure of the Standard Model. Complex numbers, which were invented to solve equations that seemed to have no real solution, numbers involving the square root of -1, numbers that seemed purely abstract and possibly meaningless, turn out to be not just useful, but apparently indispensable in quantum mechanics. Reality requires complex numbers to describe itself. Why? Why should abstract mathematics be the language of physical reality? Why should structures invented by human minds for reasons of pure logical beauty turn out to be the correct description of the physical universe? This question has no settled answer, but it suggests something extraordinary about the relationship between mathematical structure and physical reality, a relationship that points once again toward a hidden deeper layer. Physicist Max Tegmark has proposed what he calls the mathematical universe hypothesis, the idea that the universe is not merely described by mathematics, but is mathematics. Not that there is a physical universe that happens to follow mathematical laws, but that mathematical structure itself is the fundamental reality, and what we call the physical universe is one particular mathematical structure among all possible mathematical structures. In Tegmark's view, all consistent mathematical structures exist, not in the sense of being written down somewhere, but in the sense of being real, of having the same ontological status as the physical universe you inhabit. Our universe is one mathematical structure. There are infinitely many others, all equally real, all existing in a mathematical landscape of pure structure. This is the most radical version of the hidden universe theme, the suggestion that behind the physical, visible, observable universe lies not a physical substrate, but a mathematical one, a realm of pure structure and relation, of which our universe is one instance, and of which the vast majority is permanently inaccessible to any observer confined within a single mathematical structure. Whether you find this compelling or absurd probably depends on your philosophical sensibilities. But what's striking about it, what connects it to all the other hidden universe themes, is that it takes seriously something that the evidence consistently points toward. The universe has a structure that is deeper than what we can directly observe, whether that deeper structure is physical extra dimensions, holographic information encoding, quantum informational substrates, mathematical structure, or something we haven't thought of yet. The evidence consistently points toward more than what we can see, more than what we can measure, more than what our best models describe, more than 5% of the mass energy, more than what fits within the observable bubble, more than what the Standard Model contains, more than what lies within the reach of our senses. The evidence for more is overwhelming. What the more is, that is hidden. Consider the role of time in all of this, because time is perhaps the strangest hidden aspect of reality, the one that is simultaneously most familiar and most opaque. You experience time as an arrow, moving from past to future, from memory to anticipation, always in one direction. This arrow of time is the most immediate and unavoidable feature of your experience. You remember yesterday but not tomorrow. Cause precedes effect. Entropy increases. Things age. The future is different from the past in ways that feel absolute and obvious. But the fundamental laws of physics, with one important exception, are time-symmetric. The equations of classical mechanics, electromagnetism, quantum mechanics, and general relativity all work equally well if you reverse the direction of time. They do not prefer one direction of time over the other. A film of two billiard balls colliding looks physically valid whether you play it forward or backward. The laws don't care, and yet your experience of time is powerfully asymmetric. You have a past and a future. The second law of thermodynamics, entropy always increases, defines the arrow of time thermodynamically. But the second law is a statistical statement about large numbers of particles, not a fundamental law. It tells you which direction is more probable, not which direction is required. At the fundamental level, Time doesn't have an arrow. The arrow is an emergent phenomenon, arising from the statistical behavior of large numbers of particles, from the low entropy initial conditions of the universe, from the structure of complex systems. At the deepest level of physics, time may be symmetric, or may not even exist as a fundamental entity at all. Many approaches to quantum gravity, the attempt to reconcile quantum mechanics with general relativity, suggest that time is not fundamental. Loop quantum gravity, one of the leading approaches, describes the universe as a network of spin connections that evolves in a way that is not governed by an external time parameter. Time, in loop quantum gravity, is not a background against which things happen. It is an emergent, approximate macroscopic description of the evolution of a system that, at the fundamental level, is timeless. Julian Barber's radical philosophical and physical proposal goes even further. He argues that time doesn't exist at all, that the universe is a static structure of configurations, what he calls Platonia, and that the experience of time is an illusion generated by the existence of records and memories within a particular configuration. In this view, there is no now, no flow, no direction. There is only the frozen mathematical structure of all possible configurations, and the experience of time is what it feels like to be a configuration that contains memories of other configurations. If this is correct, then time, the most intimate and unavoidable dimension of your experience, is not a feature of the deep reality. It is a feature of the surface. The hidden universe is not just spatially larger than what you can see. It may be temporally different in ways that make your experience of time a local approximation of something that is, at its foundation, profoundly different. The relationship between time and information goes even deeper. One of the most profound results in theoretical physics in recent decades is the Bekenstein-Hawking formula for black hole entropy. The result that the entropy of a black hole is proportional to the area of its event horizon, not its volume. This is the result that inspired the holographic principle, and entropy in physics is a measure of information, specifically the number of distinct microstates that a system could be in while still appearing macroscopically the same. So the information content of a black hole, the complete description of everything inside it, is encoded on its two-dimensional surface. The volume hides the information, the surface reveals it. Or more precisely, the surface is where the information lives, and the volume is the projection. And this formula, this relationship between area and entropy, between surface and information, between the visible and the hidden, appears to be a fundamental feature of reality, not just a property of black holes. The holographic principle extends it to the entire universe. The information content of any region of space is bounded by the area of the region's boundary, not its volume. Reality is, in a deep informational sense, two-dimensional. The three-dimensional world you experience is a projection of information encoded on a lower dimensional surface. The depth is hidden. The surface is real. You are walking through a projection and experiencing it as depth. All of this, the dark matter, the dark energy, the quantum uncertainty, the measurement problem, the holographic principle, the fine-tuning, the limits of observation, the hidden dimensions, the emergent time, the informational foundations, all of it converges on a single, coherent, and deeply strange picture. The universe you see is a surface. It is a rendering, a projection, a broken symmetry, low-energy approximation of something more fundamental, more symmetric, more complex, and more hidden. The visible universe, the 5% you can observe, the slice of electromagnetic reality that your senses and instruments respond to, is the skin of something far larger, far stranger, and far more deeply structured than anything your instruments can directly reach. And you, the observer, the one asking these questions, the consciousness sitting in the center of this inquiry, are yourself part of this surface. You are made of the 5%. You perceive with biological instruments tuned to the surface. Your brain constructs a model of the surface, filtered for utility, compressed for efficiency, optimized for survival rather than truth. You are, in the most literal sense, a surface creature trying to understand a universe with depth you were not built to see. And yet, and this is the extraordinary thing, the thing that makes this moment in history so strange and so significant, you are beginning to see it. Not directly, not fully, but the instruments you have built are picking up signals from the hidden layers. The anomalies in the rotation curves of galaxies, the acceleration of the cosmic expansion, the patterns in the microwave background, the muon's strange magnetic moment, the tensions in cosmological measurements, the gravitational wave background humming in the geometry of spacetime. These are not failures of science. They are science succeeding at something extraordinary, detecting the edges of its own blind spots. Like a person who has spent their whole life in a room and has finally found the seams in the wallpaper where the door is hidden. You can't see the door yet, but you can feel the edges. You can feel that there is something there that the surface isn't telling you. The anomalies are not noise, they are a message. And the message is, there is more. The history of science is, in a very deep sense, the history of discovering that there is more. Every time we thought we had reached the final layer, the atom, then the nucleus, then the proton, then the quark, there was always something beneath it. Every time we thought we had mapped the universe, the solar system, then the galaxy, then the local group, then the observable universe, the universe turned out to be larger, stranger, more structured than our previous map allowed. The pattern of discovery is not random, it is systematic. Every major scientific revolution has revealed a hidden layer, a deeper, more fundamental, more counterintuitive level of reality that was present all along but not accessible to the previous framework. Newtonian mechanics hid special relativity. Special relativity hid general relativity. Classical physics hid quantum mechanics. Each layer, when revealed, was not a refinement of the previous layer. It was a restructuring, a revelation that the previous layer was an approximation, a surface phenomenon, a low energy limit of something more fundamental, and each new layer was, before its discovery, completely inaccessible to the framework of the layer above it. The people who believed Newton was complete, who believed classical mechanics was the final word, were not being foolish. They were being consistent with everything their framework could see. They couldn't see the next layer, not until the anomalies accumulated, not until the edges of the blind spots became visible, not until the seams in the wallpaper became impossible to ignore. We are at one of those moments right now. The anomalies are accumulating. The tensions in our models are sharpening, not resolving. The Hubble tension persists and grows. The muon anomaly has been confirmed and stands. The gravitational wave background has opened a new observational window. The LHC found the Higgs, but nothing beyond it, suggesting the next layer is further up in energy than we can currently reach. The cosmic microwave background shows alignments that don't fit the standard model. Dark matter has not been directly detected despite decades of increasingly sensitive searches. Dark energy remains a complete mystery. The information paradox has not been resolved, only reframed in increasingly sophisticated ways. The measurement problem in quantum mechanics has persisted for a century without consensus. The cosmological constant problem represents the largest discrepancy between theory and observation in the history of science. None of these are going away. All of them are getting more precisely defined. The edges of the wallpaper are becoming sharper. The hidden door is becoming more visible. We haven't found the handle yet, but the shape of the door is beginning to emerge. There is a question that arises here, a question that sits at the intersection of science and something harder to name, something closer to the existential weight of the situation. The question is this: why? Not why in the explanatory sense. Why does dark matter have the density it does? Why does the fine structure constant have the value it has? But why in the deeper sense? Why is the universe structured such that so much of it is hidden from observers inside it? Why is the universe opaque to its own inhabitants in so many ways, at so many scales? This is not a scientific question in the traditional sense because it asks about purpose or structure at a level above physics. But it is a question that the evidence demands be asked because the hiddenness is not random and not uniform. It has a character. The universe hides its foundations behind phase transitions. It hides its full mass behind darkness. It hides its quantum nature behind the act of measurement. It hides its informational structure behind three-dimensional appearance. It hides its past behind an opaque wall at 380,000 years. It hides its extent behind event horizons. It hides its sister universes behind inflating voids. Every layer of reality seems designed, or arranged, or structured to be invisible from the layer above. Why? One answer, grounded in physics, is that the hiddenness is a consequence of complexity. Complex systems always hide their foundations from their surface behavior. You cannot read Shakespeare's Hamlet from a description of the neurons in the brain of someone reading it. You cannot read the genetic sequence of a tree from the appearance of its leaves. The surface is connected to the foundation, but does not directly display it. Complexity inherently creates opacity between levels. And the universe is enormously complex. More complex by far than any other system we know about. So its hiddenness might simply be the inevitable consequence of its complexity. The deeper layers are hidden, not because they're kept secret, but because the relationship between levels in complex systems is always such that the surface conceals the foundation. The universe is not hiding from you, it is simply being complex. Another answer, more speculative but deeply interesting, is that the hiddenness is a structural necessity, that it is impossible for an observer embedded in a system to have full access to the system's foundations. This is Gödel's shadow falling over physics. Any observer who is part of the universe is subject to the universe's physics, including the uncertainty principle, the speed of light, the event horizon of their observable bubble. An observer inside cannot step outside to get a complete view. Full transparency would require a view from outside, and there is no outside. Or if there is an outside, it is precisely the hidden layer, the one you can't access from inside. The universe's hiddenness in this view is not a contingent feature that a more advanced civilization could overcome. It is a structural feature of being an inside observer. The universe is hidden from you the way the future is hidden from you, not because someone is keeping a secret, but because the structure of the situation makes full access impossible from your position. A third answer, the most unsettling and the most difficult to evaluate, is that the hiddenness is informative, that it is telling you something about the nature of what is hidden, the specific pattern of what is hidden, foundations rather than surfaces, substrates rather than emergent properties, the generating layer rather than the generated layer, is consistent with the idea that what is hidden is something simpler and more fundamental than what is visible. Reality appears to hide its simplicities behind its complexities. The underlying unified theory, if it exists, would be more symmetric, simpler, more mathematically elegant than the broken, complex, multi-layered reality we observe. What is hidden is the original music. What we can hear is the echo, reflected and distorted and fragmented by the complexity of the medium through which it has traveled. The universe may be hiding its simplicity behind its complexity, its unity behind its diversity, its fundamental nature behind its emergent layers. And what that would mean, if you could see through all the layers, if you could peel back every surface and find the foundation, is something that even the most speculative theoretical physics hasn't fully articulated, because the language for it doesn't yet exist. You have been on a long journey through the evidence, through the physics, through the philosophy, and through the mathematics. You have visited the flat rotation curves of galaxies spinning too fast for the mass you can see. You have stood at the edge of the cosmic horizon and looked out at the curtain that physics itself has drawn across the rest of existence. You have descended into the quantum world and found that the most fundamental layer of reality refuses to be fully defined, refuses to be fully measured, refuses to be fully seen. You have looked at the oldest light in the universe and found patterns in it that nobody can explain. You have traced the shape of a universe that is 95% invisible, that hides its foundations behind phase transitions, that encodes its information on surfaces rather than volumes, that may project its three-dimensional appearance from a two-dimensional substrate you will never directly touch. You have followed the mathematics into extra dimensions and parallel branes and holographic boundaries and informational substrates, and in every direction the mathematics has pointed the same way. Deeper, always toward something more fundamental that lies just beyond the reach of what can be directly seen. And somewhere in the middle of all of this, something has shifted. Not in the science. The science was always pointing this way, always accumulating these anomalies, always sharpening these tensions. What has shifted is the recognition that the anomalies are not isolated, that the tensions are not coincidental, that the pattern of hiddenness running through every scale and every domain of physics is not a collection of separate problems waiting to be separately solved. It is a single, coherent, consistent message from the universe about itself, a message that says, "You are inside me, and I am larger and stranger and more deeply structured than you have been able to see." The message has been there all along, written in the flat rotation curves and the accelerating expansion and the quantum uncertainty and the cosmological constant problem and the alignment of the microwave background. It has been there in the moon's strange magnetic moment and the black hole information paradox and the gravitational wave background humming through the fabric of space-time. It has been there in the structure of your own perceptual system, which shows you a surface and calls it reality. The message has always been there. You are only now beginning to read it. The reading is not complete. It may never be complete. There are limits on what an observer inside a system can know about that system, and some of those limits are structural, written into the physics of the universe at a level that no instrument and no theory will ever overcome. The cosmic horizon is real and permanent. The quantum uncertainty is real and fundamental. The broken symmetries of the low-energy universe are real and irreversible. Some of the hidden layers will remain hidden, not because science is not advanced enough, but because the architecture of reality has placed them behind barriers that exist at the level of causality itself. You will never see inside a black hole. You will never receive information from beyond the cosmic horizon. You will never directly observe what happened before the universe became transparent. You will never hold a dark matter particle in your hand and examine it with your eyes. Some of the hidden things are hidden permanently by the very structure of the universe that hides them. But other things, other hidden layers, are becoming visible. Gravitational wave astronomy has just opened a new window, and through it we are beginning to see the universe's dark and violent history written in the geometry of space-time rather than in light. Future experiments, more sensitive dark matter detectors, more precise measurements of the CMB, more powerful particle accelerators, space-based gravitational wave observatories will sharpen the anomalies and either resolve them or deepen them. And if history is any guide, if the pattern of scientific revolutions tells us anything, what lies on the other side of the current anomalies is not a minor correction to existing theory. It is a restructuring, a new layer, a new framework that will make the current one look the way Newtonian mechanics looks from the vantage point of quantum field theory, correct within a limited domain, but a surface approximation of something more fundamental, more strange, more counterintuitive than anything the previous framework could have predicted. What will that new framework look like? Nobody knows. It may involve a new understanding of space and time as emergent phenomena. It may involve a deeper understanding of the relationship between information and reality. It may involve the detection of gravitational signatures from dark matter that finally reveal its nature. It may involve a theoretical breakthrough that resolves the tension between quantum mechanics and general relativity, the two great pillars of modern physics that have coexisted for a century without being reconciled into a single coherent framework. It may involve something that nobody has thought of yet, a concept as foreign to current physics as quantum mechanics was to classical physics, a framework that will require new mathematics, new intuitions, new ways of thinking about what it means for something to exist and to be observable. Whatever it is, it will be more hidden than what we currently see, and more revealing. It will show us a deeper layer, and in doing so will show us how much more is still hidden beneath that layer. Every answer in physics has always led to deeper questions. Every revealed layer has always shown the existence of a layer below. There is no reason to think the next revolution will be the last. The universe does not appear to have a final layer, or if it does, it has hidden it very well. And so you find yourself here, at the end of this long unfurling of evidence and implication, carrying something different than when you started. Not an answer. There is no answer. Not yet, not fully. But a different relationship to the question, a recognition that the universe is not a puzzle nearly solved, not a picture nearly complete, not a story nearly finished. It is something stranger and larger and more hidden than that. The 5% you can see, the stars and galaxies and nebulae and planets and atoms and molecules that fill every photograph, every textbook, every popular science documentary ever made, is the foam on the surface of something you have no name for yet. The 95% is not background noise. It is the majority of everything. It is the context in which the visible 5% floats. And behind the 95%, behind the dark matter and dark energy and quantum fields and holographic surfaces and informational substrates, there may be more. There probably is more. The mathematics keeps pointing to more. The anomalies keep suggesting more. The universe keeps refusing to be finished. There is a particular kind of courage required to sit with this, to hold the knowledge of how much is hidden without either dismissing it or being paralyzed by it. The temptation in one direction is to minimize, to say that the mysteries are merely technical, that they will be solved with better instruments and more computation, that the universe is fundamentally knowable and we are simply making progress. The temptation in the other direction is to catastrophize, to say that the hidden universe invalidates what we know, that science is hopeless, that the darkness is too complete for any light to penetrate. Both of these responses miss the point. The hidden universe does not invalidate the visible one. The 5% we can see is real, and the science that describes it is genuine and powerful, and one of the greatest achievements of the human mind. But it is not everything. The visible universe is a window, and windows are not walls. A window shows you something real, something true, something outside. But a window also frames what you see, and the frame is not the world. Outside the frame, the world continues. The universe is not hiding something the way a person hides a secret, with intention and purpose and a moment of eventual revelation. It is hiding something the way depth hides beneath the surface, always present, always real, always exerting its influence on what you can see, but not directly accessible from the surface itself. You can feel the depth. You can measure its effects. You can trace the shadows it casts on the surface world, but to reach it directly, to stand in it and look around, requires something you do not yet have, perhaps something that cannot be built, perhaps something that can. The history of science says, something that cannot be built now has a way of becoming something that can be built later. The history of science says, the impossible observation of one generation becomes the routine measurement of the next. But history also says, every new generation of observation reveals not just what was hidden, but a new horizon of what remains hidden still. The universe does not run out of depth. It does not bottom out. Every floor reveals a basement, and every basement reveals another staircase leading down. So where does that leave you? Standing at the edge of the observable, looking out at the curve of the cosmic horizon, aware that beyond it the universe continues in all directions, possibly forever, filled with matter and energy and structure, all of it real, all of it physical, all of it subject to the same laws that govern the atoms in your body, and all of it permanently beyond any signal you will ever receive. Standing at the quantum level, looking at the indeterminacy of the most fundamental things, aware that the universe at its smallest scales refuses to be fully defined, refuses to reveal its full state, maintains a fundamental privacy that no measurement can violate without changing what is measured. Standing at the level of dark matter and dark energy, aware that the majority of the universe's mass and energy is invisible to every instrument built from electromagnetic interaction, invisible not because it's obscured, but because it doesn't speak the language of light. Standing at the level of your own perception, aware that your brain constructs a model rather than recording reality, aware that the model is optimized for survival rather than truth, aware that what you see when you open your eyes is a rendering, a representation, a surface that has been curated by billions of years of evolution for usefulness rather than completeness. You are standing inside a universe that is hiding itself from you, not maliciously, not arbitrarily, but structurally, necessarily, deeply, at every scale from the quantum to the cosmic, in every domain from particle physics to cosmology to neuroscience to information theory. The universe's hiddenness is not a flaw in the universe. It is a feature of the relationship between an observer and the reality that contains the observer. It is what it looks like from the inside of something that has no outside accessible to those inside. It is what it feels like to be a surface creature in a universe with infinite depth. And the fact that you have noticed, the fact that the anomalies have accumulated enough, the fact that the instruments have become sensitive enough, the fact that the mathematics has become sophisticated enough to begin tracing the outline of the hidden layers, that is not nothing. That is, in fact, extraordinary. You are the universe beginning to see its own hiddenness. You are the 5% starting to suspect the 95. You are the surface starting to feel the depth beneath it. And the question that remains, the question that cannot be answered here, that cannot be answered now, that may not be answerable within the current framework of human knowledge or within the current reach of human instruments, is not whether the universe is hiding something. It is hiding something. The evidence for that is overwhelming, consistent, and growing. The question that remains is what? What is the 95%? What is the deeper structure that the mathematics keeps pointing toward? What is the substrate from which spacetime emerges? What is the principle that fixes the fundamental constants? What is beyond the cosmic horizon? What happens inside a black hole? What collapses the wave function? What drove inflation? What is dark energy at its most fundamental level? What is the hidden layer beneath the standard model? What is the relationship between consciousness and quantum measurement? What was there before the Big Bang, in the opaque era before the universe first became transparent to light? These are not rhetorical questions. They are not questions with no answer. They are questions with answers, answers that exist, that are real, that are encoded in the structure of the universe itself, answers that the universe has been carrying since its first moment, answers that you can feel the edges of, that your instruments are beginning to brush against, that your mathematics is beginning to circle, but the answers are not here yet. And the most honest and most important thing that can be said, the thing that distinguishes genuine inquiry from the false comfort of premature resolution, is that we don't know, not yet. The universe is hiding something. The universe has been hiding something for 13, 8 billion years. Through every phase transition and symmetry breaking and horizon crossing and quantum measurement and emergent complexity that brought you to this moment. It has been hiding it through every civilization that looked up at the night sky and built stories about the lights overhead. It has been hiding it through every scientific revolution that peeled back one layer only to reveal another. It has been hiding it through every experiment that confirmed the standard model and every anomaly that pointed beyond it. The universe has been patient. It has let you see the surface. It has let you map the 5% with extraordinary precision and beauty. It has let the mathematics of the surface point toward the existence of the depths. And now, in this particular moment of history, with gravitational wave detectors listening to the geometry of space-time, with pulsar timing arrays detecting the universe-wide hum of merging supermassive black holes, with the James Webb Space Telescope probing the first galaxies at the edge of the visible universe, with quantum computers beginning to probe the informational foundations of physics, with theoretical physicists developing mathematical frameworks that push beyond the standard model and general relativity towards something deeper. Now the universe seems to be on the verge of revealing something. Not everything, not the final answer, but the next layer, the next level, the next revealed depth beneath the surface you've been standing on. What that revelation will look like, nobody can say. It will almost certainly be stranger than anything predicted. It will almost certainly require a new framework, a new language, a new way of thinking about what it means for something to exist and to be observable and to be real. It will reveal not just a new answer, but a new set of questions, deeper and stranger than the current ones. It will show you that the universe you thought you were beginning to understand is a surface floating on a depth you hadn't imagined. It will be, as every great scientific revolution has been, both a triumph and a humbling. A triumph because you found the next layer, a humbling because the next layer reveals how much more remains hidden. And somewhere in that revelation, in that moment of seeing the next hidden thing, there will be a recognition, a quiet, profound, slightly unsettling recognition that you have been here before. That this feeling of standing at the edge of the visible, looking out at the shape of the hidden, aware that what you can see is only a fraction of what exists, is not a feeling that goes away. It is not a feeling that resolves into certainty and completeness. It is the permanent condition of the inside observer. It is what it feels like to be conscious inside a universe that is larger and deeper and more hidden than any mind it contains can fully comprehend. You began this journey with a quiet question forming in the back of your mind, a question you hadn't quite put into words yet, a question about whether what you can see is really all there is, whether the universe is as transparent as it appears, whether the science is as complete as it sometimes sounds, whether the 5% is everything or merely the beginning. And now the question has become larger. It has absorbed the evidence, metabolized the anomalies, incorporated the mathematics, and emerged on the other side as something more precise, more urgent, and more haunting than when it started. The universe is not fully visible, not by a large margin. The hidden part is not an addendum, not a footnote, not a gap in an otherwise complete picture. The hidden part is the majority. It is the context. It is, quite possibly, the point. And we, you, are only now in this extraordinary and peculiar moment in the history of a young and curious species on a small planet in the visible 5% of a universe with no visible edges. We are only now beginning to see the shape of what is hidden, not the hidden thing itself, just its shape, just the outline of its absence in the visible world, just the shadow it casts on the surface we can see. The universe is hiding something, and we are starting to see it, not what it is, not yet, but that it is there, and that it is vast, and that the seeing, this beginning, this edge of recognition, this moment when the surface starts to reveal the depth beneath, is not the end of the mystery, it is the beginning of a much larger one. The universe has been patient for 13.8 billion years. It has given you just enough to know that there is more, and it has given you the mind to ask what the more might be. But the answer, the full, deep, fundamental answer, remains exactly where it has always been, hidden, waiting, in the dark beyond the light you can see, in the silence beneath the signals you can measure, in the depth beneath the surface you are standing on, right now, all around you, closer than you think and further than you can reach. The universe is not empty. It is full of what you cannot see. And the question of what that is, the question your instruments are beginning to ask with unprecedented precision, the question your mathematics is beginning to circle with unprecedented sophistication, the question your mind is asking right now, in the quiet space between one thought and the next, that question does not have an answer yet. But somewhere in the structure of reality, In the hidden layers beneath everything you can observe, the answer already exists. The universe knows what it is hiding. You are just beginning to learn that it is hiding anything at all. And that beginning, that first recognition of the shape of the hidden, may be the most important thing that has ever happened in the history of a species learning to see.